Imagine, just for a second, a literal lightning bolt.
Okay, wow. Starting big today.
Yeah, right. But seriously, imagine taking the immense raw energy of a lightning bolt
Right.
and then compressing it down.
Trapping it, basically.
Exactly.
Mhm.
You trap it inside a reinforced metal box, and then you bolt that box directly beneath the seat of your car.
Which sounds totally insane when you phrase it like that.
Right. But, I mean, that is not science fiction. That is literally what you are doing every single time you merge onto the highway in a modern electric vehicle.
Yeah, you're just casually cruising along, sitting on top of a massive rolling high-voltage power plant.
And it's getting even more intense, right? Like the industry is moving from these older 400-volt architectures to systems that operate at 800 volts.
Oh, easily. Or even 1,000 volts in some of the newer high-performance platforms that are coming out now.
Which is just a staggering amount of stored chemical and electrical energy. And it's positioned, just inches from your feet.
It really is.
So for anyone out there who has ever accidentally zapped themselves while trying to, I don't know, wire a simple household light switch.
Oh, yeah, we've all been there. That little 120-volt shock.
Exactly. You get that shock, and it hurts. So the obvious question immediately springs to mind when we talk about 1,000 volts. What is stopping this massive electrical force from causing an absolute catastrophe?
It's the big question.
Like if you hit a massive pothole and a single wire shakes loose, or say a well-meaning mechanic unplugs the wrong orange cable at the wrong time in a garage.
Right. Which happens more often than you'd think.
What prevents a terrifying high-voltage plasma arc or, worse, instant electrocution?
Well, it really is the existential question at the core of all electric vehicle engineering. I mean, we figured out how to harness this incredible power to propel thousands of pounds of steel and aluminum down a road at 80 miles an hour.
Which is an achievement in itself.
Absolutely. But containing that power, holding the lightning in the bottle, so to speak,
Right.
that requires a guardian.
A guardian. I like that.
And this guardian, it has to be completely invisible to you, the driver. It's constantly monitoring the physical integrity of the entire system right up until the exact millisecond it's actually needed.
And exploring the anatomy of that invisible guardian, that is our mission for today's deep dive.
You've got a really good one today.
We do. We've got our hands on this incredibly detailed master diagnostic checklist. And specifically, this document outlines what it calls the 5 dimensions of high-voltage battery safety.
It's a massive document, very technical.
Super technical. We are going to focus intensely on what the source material calls the 5th dimension, system HV execution and global safety layer.
Which sounds like something out of a sci-fi movie, honestly.
Right, and right in the center of that layer is this highly critical stop everything you are doing error code. It's designated in the sources as 503 P0A0D.
Yeah, the dreaded P0A0D.
Which, to translate into plain English, means High Voltage Interlock Loop Open, or HVIL for short.
Yeah, HGVIL. And when you see P0A0D pop up on a diagnostic scanner, it is essentially the vehicle's central nervous system absolutely screaming.
Screaming that something is wrong.
Right. It's saying that something in our physical safety chain is broken, and we need to shut down the rolling power plant right now before someone gets killed.
Okay, so let's unpack this, because reading through this technical specification, P0A0D, it isn't just a simple line of code in the software.
Not at all.
It actually represents an entire philosophy of mechanical and electrical safety. We're going to look at the 5 dimensions of this interlock loop today.
It's a great breakdown.
We'll start with the root causes, right?
Yeah.
Like, why does this safety circuit break in the first place? Then we'll explore the architecture.
Right, looking at how the vehicle's brain actually spots the brake, even when there's massive electrical interference.
Exactly. Then we'll dig into the DFMEA, which is a fancy acronym for how engineers physically design the system to prevent these failures.
And that's followed by the PFMEA, which looks at how they build it flawlessly on the factory floor.
And finally, we will look at the DVP&R, which is basically the absolute torture testing they put these systems through to prove they can survive the real world.
That is the perfect roadmap, because honestly, to truly appreciate the cure here,
The fail-safes and all that.
yeah, the brilliant engineering behind the fail-safes and the manufacturing, to appreciate that, we first have to thoroughly dissect the disease.
I love that framing. Dissect the disease.
We need to look at the anatomy of a failure. This critical safety loop doesn't just fail spontaneously without some sort of mechanism.
Right, there's always a reason.
Exactly. The source material outlines 4 fundamental underlying forces that are constantly trying to break this connection.
So before we get into how the car protects you, we need to know what exactly triggers this P0A0D error. Because looking at these sources, it is very rarely a simple, somebody came along with a pair of scissors and cut a wire kind of scenario.
Oh, almost never.
The real world is way more insidious than that. So let's start with the first root cause, which is probably the one we can all relate to most easily.
Oh, definitely. The human element.
Yes, humans messing things up.
Human error is the great equalizer, right? It's the eternal wild card in literally any highly complex engineering system.
You can design a perfect circuit on a computer.
But eventually, a human hand has to assemble it, or a human mechanic has to maintain it.
Right.
In the context of the high voltage interlock loop, human error usually enters the picture either during the initial vehicle assembly at the factory or, later on when a technician is servicing the vehicle.
And the sources point specifically to these massive connectors, like the fast-charging plugs or the connections to the motor controllers.
Or the manual service disconnect, the MSD.
Right, the big, usually bright orange physical switch that mechanics pull to essentially safe the battery before they do any work on it.
Yeah, and because these connections handle lethal amounts of voltage, they aren't just like simple friction-fit plugs.
Like a headphone jack or something.
Exactly. You can't just pop them in and pull them out easily.
Yeah.
They feature a secondary physical manual latch on the housing.
So you push the plug in, and then you have to manually flip a lever or push a locking tab to actually secure it.
Right. And the failure occurs when the technician, or maybe the assembly worker on the line, pushes the plug in, feels a bit of physical resistance.
And they just assume it's seated.
Exactly. They assume it's seated, but they fail to slide that final physical manual latch entirely into its locking track.
Oh, man, it makes me think of closing the heavy front door to your house. You know what I mean?
Oh, that's a perfect analogy.
Like you push the door shut behind you, you hear a dull thud, and you just assume it's closed. From the sidewalk, it looks completely flush with the frame.
It might even hold up against a light breeze.
Right. But if you didn't hear the deadbolt actually click into the strike plate, it is not secure at all. A strong gust of wind will just blow it right open.
And that is precisely what is happening inside these EV collectors. When that mechanical deadbolt isn't thrown, the internal microswitches inside the connector housing, they don't fully close.
So the connection is compromised.
Yeah, or the high voltage pins themselves aren't fully deeply seated, even if the plastic housing looks perfectly aligned from the outside.
And the car's computer sees that.
It does. The system registers this as a false open signal. The metal might be barely kissing, just touching slightly, but functionally, the safety loop is compromised.
Wow. And because the pins are just barely kissing, I imagine the slightest change in the physical environment could break the connection completely.
Oh, absolutely.
Which leads us pretty seamlessly into the second root cause from the sources. And honestly, this one blew my mind.
The micro-fretting.
Yes.
Yeah.
Because it is an entirely invisible enemy. The document refers to it specifically as micro-fretting.
Yeah, this is where we move away from macro mechanics, like human hands, and get into microphysics.
Okay, break that down for me.
Think about it. A car is not a static object sitting in a climate-controlled living room. It's a massive block of metal hurtling over uneven asphalt. It's dealing with constant chassis resonance.
Right, hitting bumps, potholes.
Exactly. As the suspension absorbs the impact of those potholes or ripples or even just expansion joints on a bridge.
Those high-frequency vibrations travel up through the chassis.
Yes, they travel right up into these hard plastic connector housings.
So the housing is vibrating, which means the tiny pins inside are also vibrating.
Yes, but we are talking about microscopic movements here. Shifts on the scale of micrometers.
Micrometers, that's like incredibly small.
Barely anything. But the low voltage interlock pins inside the housing, they begin to rub against each other at these really high frequencies. And that microscopic rubbing, that is the fretting.
I mean, it sounds so harmless. They are locked inside a thick plastic plug, just vibrating slightly. Why is a micrometer of rubbing a problem?
Because of what those pins are made of and what happens when they degrade over time.
Okay, what are they made of?
Well, to ensure perfect electrical conductivity for the safety signal, these pins are often plated with precious metals, usually a very thin layer of silver or gold.
Oh, wow. I didn't realize they use actual gold in there.
Yeah, they do. But as they fret, as they rub back and forth thousands of times a minute while you're driving, that mechanical friction physically wears down the gold or silver plating.
So you are literally sanding off the protective conductive layer just by driving the car down the road.
Precisely. You're polishing it right off. And once you wear through that precious metal plating, you expose the underlying base metal, which is usually a copper alloy or maybe brass.
And I'm guessing copper and brass don't like being exposed.
Not at all. Because they're exposed to whatever ambient air is trapped inside that connector housing. And when base metal is exposed to oxygen, it oxidizes.
It rusts.
Exactly. This creates a highly localized phenomenon known as micro-arc oxidation.
So essentially, these tiny little pins rub together, they shed their shiny gold armor, and then they instantly start to rust at a microscopic level.
That's a great way to put it. And here's the fatal flaw with that. Oxidation is an electrical insulator.
Rust does not conduct electricity very well.
It doesn't conduct it at all, really. So as this microfretting and oxidation layer builds up, the contact resistance of that specific pin jumps dramatically.
It creates a bottleneck.
A massive electrical bottleneck. It goes from being a perfect, clean path for the electrons to just a total wall. The interlock signal gets distorted, or the resistance spikes so high that the signal drops out entirely in these tiny transient bursts.
And the car's brain reads that resistance spike and thinks, oh no, the circuit is broken, shut down the reactor.
Yep, it triggers the P0A0D error.
It is wild to think that a microscopic layer of rust, generated by a single micrometer of vibration, can bring a 2-ton vehicle to a complete halt on the highway.
It really highlights how sensitive these systems have to be.
But the sources don't stop there. The third root cause takes us back into the factory, like before the cars even hit a single pothole to cause that vibration.
Right, back to the assembly line.
We were looking at manufacturing sins, specifically something called terminal pushout.
Oh yeah, terminal pushout. This issue comes down to the immense precision required in modern wire harness manufacturing.
Okay, tell me about wire harnesses.
Well, inside these high voltage plugs, you have the tiny wires for the low voltage interlock loop. Those copper wires have to be physically attached to the metal terminal pins.
Right, they don't just magically connect.
And they don't solder them either. They use a mechanical process called crimping.
Right, because solder can become brittle,
Right.
And it can crack under automotive vibration.
Exactly. Solder is great for a circuit board, bad for a vibrating wire. So they crimp it.
How exactly does that work at a factory level?
Think about what a crimp actually is. It is applying immense, highly calculated mechanical force to literally cold weld the metals together.
Cold weld.
Yeah. They take the metal barrel of the terminal, they insert the stranded copper wire, and a massive machine crushes the barrel around the wire.
Just squishes it flat.
Squishes it with incredible pressure. If you look at a perfect crimp under a microscope, you don't even see individual round copper strands anymore. No. The pressure is so immense that it deforms all the strands into this solid honeycomb of copper. It completely fills the brass barrel with zero air gaps.
That sounds incredibly robust.
Yeah.
Solid honeycomb of copper. How does that fail?
It fails when the manufacturing machine is off by just a tiny fraction. If the crimping tool applies slightly too little force, or if the dies are misaligned and apply the force asymmetrically, you don't get that perfect cold weld.
You get air gaps.
You get micro gaps, and you introduce uneven mechanical stress into those copper strands. So over time, as the car drives and the wires naturally heat up and cool down, metal fatigue sets in at that specific weak point.
And the wire just breaks.
The wire starts to physically loosen, and eventually it backs completely out of the terminal barrel. That is what we call terminal pushout.
So the wire literally pulls itself out of the pin from the inside.
Exactly.
But the sources also highlight another way this pushout happens. And honestly, this is the detail that really caught my attention. It's a massive paradox.
A testing paradox.
Yes. Because during the factory assembly process, they obviously have to test these wire harnesses, right, to make sure they work before they put them in the actual car.
Absolutely. Quality control is huge, and it relies on automated test probes. The machine physically inserts a tiny metal probe into the female terminal to verify electrical continuity.
So, if I'm reading this right, the very act of testing the part in the factory can sometimes plant the microscopic seed for its destruction months later on the road.
Yes. It is the ultimate tragedy of automated quality control.
That's crazy. How does that happen?
Well, inside the female terminal, there is a tiny, highly calibrated metal leaf spring. Its entire job is to maintain constant tension against the male pin when they are finally plugged together.
Okay.
Now, if the automated factory test probe is slightly misaligned, or if the robotic arm jams it into the terminal just a fraction of a millimeter too aggressively,
Yeah, it hits that little spring.
it hits it and it permanently yields or bends that internal metal spring.
It flattens the spring right out.
Yes. And the crazy part is, it still passes the conductivity test in the factory.
Because the probe is still touching the metal.
Exactly. The probe successfully made physical contact, electricity flowed, so the computer checks the box. Perfect part.
Wow.
But the test itself just destroyed the terminal's mechanical grip. So fast forward 6 months, the customer is driving their brand new EV over a washboard dirt road.
And because that spring lost its tension on the factory floor?
The male pin just rattles loose, the loop breaks. P0A0D.
That is just a painful irony.
Mm.
You test it to guarantee it is perfect, and the test is the exact mechanism that introduces the fatal flaw.
It keeps manufacturing engineers up at night, I guarantee you.
I bet. So let's review. We have the human error of failing to lock the deadbolt. We have microscopic vibration wearing away gold plating. And we have manufacturing defects from misaligned crimps and heavy-handed test probes.
Those are the physical problems.
Exactly. Those are all physical issues. But the fourth root cause the sources outline. But this is entirely different. It feels almost like science fiction.
Because there's no physical break.
Right. The wire doesn't even have to physically break. The document calls it EMI, or electromagnetic interference.
Yeah, EMI. This is a uniquely modern problem, and it is a direct side effect of the incredible performance capabilities of today's electric vehicles.
Okay, unpack that for me. How does high performance cause EMI?
To manage 800 or 1,000 volts and to push literally hundreds of horsepower to the wheels efficiently, the vehicle's inverters have to use highly advanced semiconductors.
The inverter, just as a quick refresher for the listener, is the component that takes the direct current, the DC power from the battery, and turns it into alternating current, the AC power, that actually spins the electric motors.
Perfect definition. And specifically, the industry has largely shifted to materials like silicon carbide, or 6E, and highly advanced insulated gate bipolar transistors, or IGBTs.
Okay, lots of acronyms,
Yeah.
but what do they actually do?
They switch power fast. To create that alternating current, the inverter switches the power on and off at incredibly fast speeds. We are talking about tens of thousands of times per second.
That is fast.
With silicon carbide in particular, the speed at which the voltage switches from 0 to 1,000 volts and back is staggering. In physics terms, this is a very high rate of change in voltage and current over time.
The document calls that high DVDT and DID.
Yes, high DVDT and DID.
Okay, let me pause you there because we need to translate DVDT into the real world for a second. If I remember my high school physics, we're talking Maxwell's equations and Faraday's law of induction here.
Oh, look at you pulling out Faraday.
I try. But basically, whenever you have a rapidly changing electric current moving through a wire, it creates an expanding and collapsing magnetic field around that specific wire.
Your high school physics teacher would be proud. That is spot on. And the faster that voltage changes, the higher that DVDT is, the more aggressive and far-reaching that magnetic field becomes.
So we have these massive orange high-voltage cables carrying this rapidly switching backflow currents, right?
Right.
Which means they're generating this intense, pulsing magnetic field all around themselves. And right next to them, literally running through the same physical connectors, we have our tiny little low-voltage interlock safety wire.
Which acts perfectly as an antenna.
An antenna.
Exactly. As that aggressive magnetic field from the high-voltage lines cuts across the low-voltage safety wire, Faraday's law dictates that it physically induces a voltage inside the safety wire.
It creates a phantom current.
Yes. It creates a current that shouldn't be there. We call this common mode noise in the industry.
It's literally generating fake electricity in our critical safety loop.
It is. Now, historically, an interlock loop was just a simple low-voltage direct current, just a basic DC signal.
Like a flat 5 volts.
Yeah, the car's computer sent out a steady 5 volts. If it got 5 volts back on the return wire, it knew the wire was intact. If you looked at it on an oscilloscope, it was just a flat line.
Super simple. But if that pulsing magnetic field is inducing a phantom voltage, that flat line isn't flat anymore, is it?
Not even close. It becomes incredibly chaotic. The pure 5-volt DC signal gets completely overwhelmed by these high-frequency spikes that are oscillating wildly.
It's garbage noise.
Complete electrical garbage. The battery management system, the BMS, is sitting there expecting a clean, steady DC signal. Instead, it gets hit with a wall of chaotic magnetic-induced noise.
And because the BMS can't find that clean, flat signal hidden in all that noise, it just assumes the circuit must be broken,
Right. It plays it safe.
and it triggers a false P0A0D error.
Yeah.
It shuts down the whole car, even though the wire is physically perfectly intact.
Exactly.
It's like trying to listen to someone whisper a specific secret password to you while you're standing next to the speakers at a heavy metal concert or next to an industrial jet engine.
That's a really good visual.
Like, the whisper is technically still happening, right?
Yeah.
The sound waves are hitting your ear. But the acoustic energy of the jet engine completely overbends your eardrum.
You can't separate the signal from the noise.
Right, so you just assume the person stopped whispering entirely.
That is exactly what happens electrically here. The signal integrity is destroyed not by a physical break, not by rust, but by completely invisible induced magnetic fields.
Okay, so this creates a massive engineering puzzle.
A huge one.
Because if the magnetic fields from the inverter are inducing phantom voltages and screaming over our signal,
Yeah.
and if microscopic vibrations are trying to rust our pins,
Right.
and if human mechanics are forgetting to lock the clips, well, a simple, continuous DC electrical current is clearly utterly insufficient to act as our safety tripwire.
It's just too vulnerable.
Which leads us into the second dimension of our sources. Knowing all these physical and magnetic forces are actively conspiring to break or spoof the connection, how do the engineers redesign the brains of the system to fight back?
And this is where we transition from understanding the physical failures, the disease, into exploring the architecture of the failsafe, the cure.
The vehicle's brain.
Yes, primarily the BMS and the vehicle control unit. They have to meet incredibly strict global automotive safety standards. Specifically, a standard known in the industry as ISO 26262 SLD.
Let me decode that for the listener. ASIL stands for Automotive Safety Integrity Level, and ASLD is the highest, most stringent classification possible.
It is the absolute top tier.
It is reserved for systems where a failure could result in severe, life-threatening injuries.
Which high-voltage electrocution certainly qualifies for.
Definitely.
Because the stakes are ASLD, the vehicle's response cannot be simple. It can't be easily fooled. It requires a highly synchronized, incredibly fast dance between software algorithms and physical hardware to diagnose the fault and execute a safe response.
So let's look at how they solve that magnetic induction problem first, the jet engine problem. Because as we established, the pure DC signal is just too easily drowned out or spoofed.
Right. So if you can't use a steady DC voltage as your tripwire because the magnetic fields keep messing with it, what do you use instead?
Yeah, what's the solution?
You change the language the system speaks.
Change language.
They ditch the static DC signal entirely, they throw it out, and they move to a dynamic PWM square wave.
PWM. That stands for pulse width modulation, right?
Exactly.
I've seen PWM used in things like dimming LED lights or controlling computer fans. What does it look like in this specific context?
Instead of a steady flow of 5 volts, the BMS rapidly pulses the voltage on and off. 5 volts, 0 volts, 5 volts, 0 volts.
Just pulsing it.
Yeah. And if you look at it on an oscilloscope, instead of a flat line, it looks like a series of perfectly square boxes, a square wave.
So it's not just a constant current. It is a rhythmic digital heartbeat.
A heartbeat is the absolute best way to visualize it. And the BMS isn't just looking for raw voltage anymore. It doesn't just care if there's power. It is constantly monitoring 2 highly specific metrics of this heartbeat.
Okay, what are they?
First, the frequency, how fast the pulse beats, say exactly 1,000 times a second.
Got it.
And second, the duty cycle, which is the exact ratio of how long the pulse stays on versus how long it stays off during each individual beat.
It's like a percentage.
Exactly. For example, it might be on for 20% of the time and off for 80%.
So why is this square wave, this specific heartbeat, so much more resilient than the steady DC signal?
For 2 critical reasons. First, it completely solves the EMI jet engine problem.
How so?
Because the random chaotic magnetic noise from the inverter, it cannot accidentally replicate the exact mathematical frequency, AND, the precise duty cycle of the PWM heartbeat.
It's just random noise.
Right. So the BMS applies a digital filter. It essentially ignores all the raw voltage spikes, all the chaos, and it only listens for that specific 20% duty cycle rhythm at exactly 1,000 hertz. It cuts right through the noise.
It's like having a secret knock.
Eh.
The jet engine is making a ton of noise, but the computer is only listening for tap, 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 tap. The random noise simply can't fake the complex knock.
That is perfectly said. And the second reason is physical security against short circuits.
Okay.
Imagine a scenario where the interlock wire rubs against the metal chassis and gets frayed, exposing the bare copper wire.
So the plastic insulation is worn away.
Right, and let's say that bare wire touches a grounded metal part, or maybe it accidentally crosses with another random 12-volt power line in the wiring harness.
Okay, a short circuit.
If you were using the old simple DC system, the computer might read that stray incoming 12 volts and think, oh, hey, I see voltage, the loop must be intact.
It gets spoofed by the short circuit. It thinks everything is fine.
Exactly. But with the PWM heartbeat,
Oh, I see where this is going.
if that frayed wire touches a steady voltage source, the heartbeat instantly flatlines. The square wave is physically destroyed. It just becomes a solid, steady voltage.
Right.
The BMS immediately sees that the exact frequency and duty cycle are gone, recognizes that the system has been short-circuited or spoofed, and instantly throws the P0A0D error.
That is brilliant. It demands the secret password to be spoken in a very specific, unfakeable rhythm. Any deviation, and it shuts it down.
Exactly.
Oh, wait, hold on. Let's go back to our microfretting and vibration problem. The car is hitting potholes, right? If I hit a massive bump and the physical pins inside the connector literally jump apart for just a tiny fraction of a millisecond, does that interrupt the PWM heartbeat?
It absolutely does. The physical continuity is momentarily lost, so the heartbeat drops a beat.
But if the system reacted instantaneously to every single microsecond signal drop, you would never be able to drive down a rough dirt road.
No, you'd be stranded immediately.
The car would constantly be throwing error codes and shutting down on the highway. And honestly, losing your power steering and propulsion in the fast lane because you hit a bump, that is a massive safety hazard in itself.
You've just identified the core tension in functional automotive safety. You are constantly balancing the risk of electrical electrocution against the kinetic risk of causing a high-speed traffic accident.
So how do they solve it?
To solve this, the engineers introduce what we can call software patience, specifically a 150 millisecond debounce filter.
Debounce. That sounds like a term from digital signal processing.
Yep.
How does it work in the car?
It works exactly like a digital sampling filter. The software in the microcontroller is programmed to wait and verify. The instant the PWM heartbeat drops out, a clock starts ticking in the software.
A countdown timer.
Yep. The system waits for exactly 150 milliseconds, and during that time, it keeps sampling the line.
It's like a radar system seeing a momentary blip on the screen. It doesn't instantly launch the missiles, right? It waits for the next sweep of the radar to see if the blip is actually still there, or if it was just, a flock of birds.
That's a great analogy. If the PWM signal comes back clean before that 150 millisecond timer expires, the software chalks it up to a pothole, or a transient vibration bounce, or a stray EMI spike.
It decides the birds aren't a threat.
Right. It clears the timer, resets, and lets you keep driving. You never even see a warning light on your dash.
The software decides the threat wasn't real. That's patience.
But, and this is the absolute red line, if the signal is still gone at millisecond 151, the software determines that this is not a pothole, this is a hard fault. The patience runs out, and it declares a confirmed P0A0D error.
Okay, so the debounce filter elegantly handles the rough roads and the transient glitches. That makes perfect sense. But looking further into the sources, there is a completely different architectural response for what the document calls a fatal event.
Yes, the worst case scenarios.
Right. Because software patience is fantastic for potholes. But what if you are in a massive, catastrophic collision? Or what if a mechanic doesn't just bump a wire, but literally grabs the manual service disconnect and violently yanks it completely out of the car while the system is fully energized?
In those extreme scenarios, you simply cannot afford software patience. 150 millisecond delay while a live high-voltage cable is sheared in half in a crash, that could mean a lethal electrical fire before the software even decides to act.
Right. Fire moves fast.
Furthermore, in a massive crash, you cannot even rely on the software microcontroller, the MCU, to process the data.
Why not?
Because the MCU itself might have been crushed, or it might have lost its own 12-volt low-voltage power supply in the impact. You need something faster and far more primitive than software. You need a reflex.
A reflex. Like when you accidentally touch a hot stove. Your hand jerks away before the pain signal even travels all the way up your spine to your brain to be consciously processed. The spinal cord just acts.
That is the exact biological equivalent of what they build here. Alongside the software, the engineers design a completely independent, hardwired override.
Hardwired.
Yes. It uses analog comparator circuits built directly onto the physical circuit board of the BMS. It bypasses the software processors entirely.
So it doesn't need to run code to make a decision.
No code at all, just raw physics and simple logic gates. If the interlock signal drops and the vehicle simultaneously detects a crash flag like the airbags deploying, or if the hardware detects the massive, instantaneous voltage collapse of an MSD being ripped out, this hardware comparator circuit acts independently.
What does it do?
It physically cuts the control power to the main contactor coils.
Okay, let's define contactors to the listener really quick.
All right.
These aren't solid-state microchip switches, right? They are massive, physical, clunking relays.
Yes, very physical. Inside the main battery pack, there are heavy-duty electromagnetic switches called contactors. They are the actual physical bridge that allows the high-voltage energy to leave the battery pack and enter the rest of the car.
Right.
When they are energized, a powerful electromagnet pulls a heavy copper bar across two terminals, physically closing the circuit.
And when you cut the low-voltage power to that electromagnet,
A massive mechanical spring violently snaps the copper bar back, physically severing the high-voltage connection. The hardware override reflex forces those contactors to open in under 50 milliseconds.
oh, good.
Boom! Total physical galvanic isolation of the high-voltage system. The battery is sealed off, completely independent of whatever the software might be trying to calculate.
So we have software patience for the bumps and a lightning-fast hardware panic reflex for the disasters. But let's look at the gray area in between those two extremes. What happens when the car confirms a normal error? Say you are just driving along, you don't crash, but a wire completely shears off due to fatigue. That 150 millisecond software timer runs out. Does the computer just violently blow the contactors open while you are cruising?
This brings us to what the sources call smart shutdown logic.
Smart shutdown logic.
Right. It requires context-aware safety. The system has to react entirely differently depending on the kinetic state of the vehicle at that exact millisecond.
The kinetic state, like how fast it's moving.
Exactly. The logic is divided into static and dynamic fail-safes.
Walk me through the static scenario first.
Static is the key-on state. You walk up to your EV in the driveway, get in, and press the start button. Before the car ever closes those main contactors to supply high voltage to the motors, it runs a pre-flight diagnostic check.
Like an airplane.
Just like an airplane. If it detects the P0A0D error during the startup phase, the response is absolute and unforgiving.
Because you are parked, there is zero kinetic risk to stopping you.
Exactly. The main relays simply refuse to close. The vehicle immobilizes itself entirely. You cannot put it in drive, you cannot plug it into a fast charger. The dashboard lights up with warnings, and the car becomes a very expensive paperweight until it is towed and repaired.
It prioritizes electrical safety 100%. That makes total sense.
It does.
But dynamic. Dynamic is the nightmare scenario. You are driving 70 miles per hour in the passing lane on a crowded interstate, and a wire snaps. The interlock loop opens. What happens?
If the system applied the static logic and immediately severed the high voltage power at 70 miles per hour, the vehicle would instantly lose all propulsion.
Which is terrifying.
It gets worse. Depending on the specific EV architecture, you might also rapidly lose your electronic power steering assist or your power braking assist.
Which means you suddenly become an unpredictable, heavy, unsteerable brick moving at highway speeds.
Yeah.
You're highly likely to cause a massive rear-end collision or just lose control entirely.
Exactly. Which means cutting the power to prevent a potential electrical accident directly causes a fatal kinetic accident. The smart shutdown logic recognizes this impossible choice. So if the signal drops while driving, it compromises. It does not immediately cut the main contactors.
How does it manage the risk then if the wire is broken?
Instead of a hard shutdown, the BMS issues highest priority warnings to the driver. We're talking flashing red and yellow malfunction lights, audible alarms screaming in the cabin.
Letting you know things are very bad.
Very bad. And simultaneously, it strictly curtails the available charge and discharge power of the battery. We call this the SOP, or state of power limit. It might aggressively cut your available power by 50% or more immediately.
So it essentially forces the car into a severe limp home mode.
Yes. It leaves you just enough electrical power to maintain control, steer, brake, and safely navigate your way to the shoulder of the highway. But the vehicle is aggressively, noticeably forcing you to pull over. You can't just keep cruising at 70.
Okay, and once you do pull over?
The system is constantly monitoring the wheel speed sensors. The absolute second those sensors register 0 miles per hour, the exact moment you come to a complete stop. The dynamic logic transitions seamlessly back to static logic.
And then it kills it.
Then it kills it. The contactors instantly snap open, the high voltage power is severed, and the system permanently locks you out. It will not allow you to put the car back into drive.
Wow. It guides you to kinetic safety before shutting down the electrical reactor.
It's a very elegant balance.
That is just incredible situational awareness. It balances physics with human behavior perfectly. Okay, so the digital architecture and the logic are undeniably brilliant. The synchronized dance between PWM signals, software debounce filters, and hardware reflexes. It's perfectly choreographed.
It looks great on paper.
Right. But, as any engineer knows, a perfect plan on a digital CAD screen is entirely useless if the physical materials can't survive the brutal reality of the physical world.
The real world is a messy place.
It's extremely messy. So how do we literally build a system that stops these faults from happening in the first place? That brings us to Section 3 of our master document, DFMEA.
DFMEA. This stands for Design Failure Mode and Effects Analysis. It is a highly structured engineering practice.
What does that actually look like in practice?
Basically, you put a team of highly pessimistic engineers in a room, and their entire job is to imagine every single conceivable way a physical design could possibly fail.
Just brainstorming disaster scenarios.
Exactly, and they score each failure. They score how severely bad that failure would be, how frequently it might happen in the real world, and how hard it would be to detect before it causes a problem.
And based on those scores, they mandate physical defenses.
Right. And for the high voltage interlock loop, because a failure carries the risk of lethal high voltage electrocution or a thermal runaway fire, it is assigned the absolute highest possible severity score in the entire DFMEA matrix.
Which is?
An S9.
An S9 score, which I assume means zero compromises allowed.
None. You have to design the ultimate defense.
So what is their first line of physical defense?
Spatial and material defense against our old friend, EMI. The magnetic interference. We talked about the magnetic fields from the inverter creating that high-frequency noise that spoofs the signal, right?
Yeah, the jet engine noise.
To block that, the low-voltage HVIL wires cannot just be cheap, standard copper wire. They have to be heavily shielded, twisted pair braided wires.
Okay, let's break that down because I've seen twisted wires before. Why twist the wires?
Twisting the positive and negative signal wires closely together is actually a very clever physical trick to defeat magnetic interference.
How does twisting them help?
If a magnetic field hits twisted wires, it induces a positive voltage spike in one half of the twist and a negative voltage spike in the other half. Because of the geometry, when the signals reach the computer at the end of the line, the spikes mathematically cancel each other out.
Oh, that is deeply clever. It uses the interference against itself.
Exactly.
And what about the braided shielding part?
The twisted wires are then wrapped in a tightly woven metallic braid. This braid acts as a flexible Faraday cage. It catches and grounds any external electromagnetic waves before they even reach the inner copper core.
Nice.
And finally, all of this is wrapped in heavy-duty, dual-color corrugated plastic tubes to provide 100% physical protection against abrasion from rubbing against the chassis.
Okay, I have to push back on this a bit, though.
Go for it.
I understand twisting the wires and the little braid, but if EMI from the high-voltage lines is really such a massive S9 severity problem, why not just wrap the interlock wires in significantly thicker, heavier metal armor? Why rely on just a thin wire braid?
It's a fair question. It comes down to weight, cost, and the fundamental physics of magnetic fields.
Okay.
Armor only does so much against low-frequency, high-energy magnetic coupling. And adding pounds of lead or thick steel shielding to a wire harness ruins the efficiency and range of the electric vehicle. The most effective defense against a magnetic field isn't actually armor.
What is it?
It's empty space.
Empty space? You mean just keeping them physically apart?
Yes. Magnetic field strength drops off exponentially the further you get away from the source. It follows the inverse square law.
Okay, inverse square law.
Basically, if you simply doubled the distance between the massive high-voltage cable and the tiny safety wire, you reduce the magnetic interference to a quarter of its original strength.
Oh, wow. So distance is the ultimate weightless shield.
It really is. The DFMEA specification mandates strict 3D physical isolation. The low-voltage HVIL wires are strictly forbidden from being bundled with or running parallel and close to the high-voltage silicon carbide power lines.
You literally can't put them in the same tube.
Exactly. The physical routing of the wiring harness throughout the entire vehicle chassis has to be meticulously designed in 3D CAD space to ensure these two systems remain spatially separated at all times.
That makes perfect sense. You don't build a thicker wall, you just move the house further away from the blast zone.
Exactly.
Okay, what about the physical connectors themselves? We talked earlier about human mechanics failing to latch them properly, the whole deadbolt analogy. How does a CAD design force a human to do their job correctly?
By engineering what the industry calls fortress connectors.
Fortress connectors. I like the sound of that.
These are nothing like the little USB plugs on your laptop. They utilize CPA, which stands for Connector Position Assurance, and TPA, Terminal Position Assurance.
What does that look like?
These are brightly colored secondary mechanical locking levers built directly into the heavy plastic housing.
Okay, but how do they outsmart human error, if I could just forget to push it?
Through mechanical interference design. The plug is physically molded so that the main pins cannot fully seat inside unless they are perfectly microscopically aligned. But more importantly, that brightly colored CPA locking lever physically will not snap down into its track unless the primary latch is 100% fully engaged.
Oh, I see.
If you try to force the lockdown while the plug is only 99% seated, the plastic lever physically jams. It won't move.
It mechanically refuses to let the human make a mistake. You can't fake a locked state.
Yes, and beyond the mechanical locks, they also have to survive the physical environment.
Right, the underside of a car.
The underside of a car is a brutally hostile place. You've got freezing saltwater spray in the winter, boiling mud in the summer, mechanics hitting it with industrial pressure washers.
Sounds awful.
It is. So the DFMEA specifies high specification fluoro rubber O-rings at every single joint and wire entry point in the entire connector.
To keep the water out, what is the actual waterproof rating on these things?
It achieves an IP68, and in many critical areas under the car, an IP69K sealing rating.
IP69K. That is basically the highest waterproof rating that exists in consumer goods, right?
Pretty much.
That means it can withstand close range, high pressure, high temperature steam jets from an industrial pressure washer.
Precisely. It guarantees that absolutely no external moisture, road salt, or dirt can penetrate the connector housing, which is vital because any moisture inside the housing accelerates the environmental corrosion that leads to our microfretting problem.
Speaking of moisture and microfretting, the sources detail one specific design feature regarding the main battery pack that is absolutely fascinating to me.
Oh, the Gore valve.
Yes. We're talking about the massive metal enclosure that holds the entire battery. The document introduces a component called a Gore valve, and it sounds like magic.
It's a beautiful piece of physical engineering designed to solve a very complex thermodynamic trap.
Okay, lay out the trap for me.
Think about the massive EV battery pack. When you are driving the car aggressively or when you plug it into a massive 350 kilowatt DC fast charger, the hundreds of individual battery cells inside that sealed pack generate a tremendous amount of thermal energy. They get hot.
Right, and basic physics, heat causes expansion.
Exactly. The air trapped inside the rigidly sealed metal battery enclosure heats up and expands rapidly. This drastically increases the internal air pressure pushing out against the metal walls.
Okay. And conversely, when you park the car outside in the freezing winter cold overnight,
The battery cools down, the air inside shrinks, and the pressure plummets, creating a massive vacuum inside the box.
right, and if the battery box was a completely, perfectly rigid, airtight seal, these massive daily pressure swings would eventually warp the metal casing, right?
Cool.
Or more likely, violently blow out the rubber weather seals.
Exactly, it would destroy itself. So the box cannot be perfectly sealed. It has to be able to breathe to equalize its internal pressure with the outside atmosphere.
If it breathes, it has to suck in outside air to equalize the vacuum. And outside air contains humidity. It contains moisture.
And there's the trap. If the battery sucks in humid outside air on a cold night and the internal components are cold, that airborne moisture condenses.
Just like a cold glass of water on a summer day.
Exactly. You literally get liquid water droplets forming on the inside walls of the high voltage battery enclosure. That liquid water eventually drips down, finds its way to the internal interlock pins we talked about, and suddenly you have accelerated electrochemical corrosion.
The pins rust, the fretting gets worse, and the safety signal dies.
Yep.
So you are trapped. You have to let air in so the box doesn't physically explode or collapse. But if you let air in, the water rusts the system and breaks the safety loop.
Yeah.
So how does a Gore valve solve a thermodynamic paradox like that?
The Gore valve is constructed from a microporous fluoromembrane.
Microporous fluoromembrane.
It is a highly engineered synthetic material with millions of microscopic pores. The brilliance lies in the exact size of those pores. They are precisely engineered to be large enough to allow microscopic air molecules, nitrogen and oxygen, to pass through freely. This allows the pack to equalize pressure.
God, I feel a butt coming.
But the pores are significantly smaller than the molecular structure of a liquid water droplet. So liquid water, even if it is hitting the valve under high pressure from driving through a deep puddle, physically cannot penetrate the membrane.
It is literally Gore-Tex.
It is.
Just like a high-end hiking rain jacket. It lets the vapor of your sweat evaporate out so you don't get clammy, but it completely stops the liquid rain from soaking in. They literally put a Gore-Tex jacket on a 1,000-pound car battery.
It is the exact same fundamental principle applied to an industrial automotive scale. It allows the battery to constantly breathe and balance its internal thermodynamics without ever letting liquid water inside.
That is amazing.
It fundamentally cuts off the environmental moisture supply that causes the interlock pins to corrode in the first place.
I love when high-tech digital problems are solved by brilliant physical material science.
It's the best of both worlds.
Okay, so the DFMEA phase gives us this perfect blueprint. We have magnetic spatial isolation, twisted pair Faraday cages, mechanically unfoolable fortress connectors, and breathing Gore-Tex battery packs.
A perfect design.
But, as we learned earlier with the terminal pushout problem, a perfect blueprint is entirely useless if the factory worker, or the robotic assembly machine, makes a microscopic mistake while building millions of these things a year.
Right. It has to be built right.
So how do manufacturers guarantee perfection on a chaotic assembly line?
This brings us to the manufacturing execution side, which is detailed in the PFMEA section of the sources. Process failure mode and effects analysis. While DFMEA looks at the design on paper, PFMEA looks at the reality of the factory floor. The overarching goal here is to statistically control the 5M1E variations in mass production.
5M1E, that sounds like a Six Sigma manufacturing term.
It is. It stands for man, machine, material, method, measurement, and environment. These are the 6 fundamental vectors that can introduce a defect on any assembly line. PFMEA tries to build systems that lock all 6 of them down completely.
Okay, let's go back to that human error of not fully latching the connector, the man part of 5M1E. On the assembly line, how do they fix that?
Well, locking that specific CPA or TPA latch is designated as a KCC, a key control characteristic.
Meaning, it is a critical safety step that the factory software knows cannot be skipped or done poorly.
Exactly. The human operator is trained to physically push the lock until they feel its seat and hear a distinct, satisfying click.
But we established humans are fallible.
Right. Human ears get tired on a loud factory floor, and human hands get fatigued after an 8-hour shift. You might think you heard a click, but it was the guy next to you dropping a wrench.
Right.
So PFMEA dictates that they absolutely do not trust human senses for a KCC. They engineer the assembly workstations with 100% visual and acoustic machine confirmation.
How does that actually work in practice on the line?
As the worker physically makes the connection, an automated camera system mounted above the station takes a high-resolution photograph of the connector. It uses machine vision algorithms to analyze the exact geometric position of that brightly colored locking tab.
Wow. It literally uses AI vision to visually inspect every single plug as it is made on the line.
Every single one. And it integrates directly with the factory control software. If the camera algorithm verifies the lock is mathematically fully engaged, it sends a pass signal to the manufacturing execution system, or MES.
And then what?
The MES ties that specific photograph, proving a perfect lock, to the specific digital VIN number of the car rolling down the line. So there is a permanent record.
And if the worker didn't push it hard enough, what if the AI says no?
If the camera sees the lock is even a millimeter out of place, it flags a fail. The MES literally will not allow the conveyor belt to advance to the next station. The line stops.
It physically prevents the car from being built wrong.
Yeah.
That handles the man variable perfectly.
It does.
But what about the machine variable, the microscopic stuff we talked about, like the crimping issues and the terminal pushout? Cameras can't see inside a solid metal pin.
No, they can't. That requires microscopic validation. The robotic machines that strip the heavy wires and crank the metal terminals are constantly monitored by internal sensors. The exact crimping depth, down to the micron, and the physical torque applied are strictly controlled and logged for every single wire.
But again, you can't just trust the machine's internal sensors, right?
Mm.
Machines drift out of calibration.
Exactly. They don't just trust the machine. They perform destructive, random metallurgical cross-section tests.
Would they destroy the parts they just made?
Yes. They randomly take a finished, freshly crimped high-voltage wire right off the active production line. They embed the connector in clear epoxy resin so nothing can move. Then they take a high-speed diamond saw and slice the terminal perfectly in half.
Wow.
They polish the cut surface and place it under a metallurgical microscope.
They're looking for those microscopic air gaps in the crushed copper honeycomb you mentioned earlier.
Exactly. They measure the exact compression ratio of the metal strands. If there are gaps, it means the machine is wearing out or out of alignment, and it could lead to metal fatigue on the road. If they see gaps, they stop the line and recalibrate.
That is intense.
They also do physical pull force tests on the ground terminals, hooking the finished wire up to a hydraulic machine that literally tries to rip the wire out of the pin, ensuring it meets strict physical tension requirements before it yields.
And what about the brains of the operation? The circuit boards inside the BMS that have to process those tiny PWM heartbeats.
The printed circuit board assemblies, or PCBA, undergo an incredible level of scrutiny. First, they use 100% solder paste inspection, or SPI.
What is that?
Before the microscopic microchips and resistors are even placed onto the bare board, a laser scans the tiny blobs of solder paste to ensure the exact correct volume of paste is present, down to the micron.
So they measure the glue before they place the chips.
Right. And then, after the chips are placed and the board is baked in the reflow oven to melt the solder, it goes through 3D automated optical inspection, or AOI.
More cameras.
A robotic arm sweeps lasers and high-resolution cameras across the board, scanning every single tiny solder joint in 3 dimensions.
What are they looking for?
It is looking for microscopic cracks, misalignments, or cold solders, which are joints that didn't melt perfectly, because a single cracked solder joint on the BMS board might slightly raise the electrical resistance, which could interfere with the delicate timing of that PWM heartbeat signal.
The level of microscopic paranoia is staggering.
It is absolute paranoia.
But even with diamond saws and 3D lasers, how do they know the whole system actually works together when all these thousands of parts are finally plugged into a complete car?
That requires the ultimate final exam performed at the end-of-line, or EOL station.
The end of line.
As the fully assembled, completely sealed battery pack is coming off the line, 2 massive automated tests occur. First, automated robotic test probes connect to the pack's main interfaces and check the dynamic DC resistance of the entire high voltage interlock loop.
The whole loop at once.
Yes. That means it tests every single wire, every single pin connector, every internal switch, all combined in one massive circuit.
And what is the passing grade for the entire loop?
The total resistance must be strictly less than 1.0.
1 ohm.
Yeah.
That is practically zero resistance. It's essentially a pure superconductor at that point.
It is incredibly tight. If the scanner reads 1.1 ohms, it instantly flags the pack. The system knows that a slightly higher resistance means one single pin out of dozens is slightly bent, one crimp is slightly weak, or one lock isn't perfectly seated.
And what happens to the pack?
The pack is physically intercepted, pulled off the line, and sent to a teardown rework station. It never leaves the factory.
Okay, that proves the wires work.
Yeah.
But what is the second end-of-line test?
The second test is the physical validation of the hardware panic reflex we discussed earlier, the 50 millisecond hardware bypass.
How do they test that?
They hook the battery pack up to a massive testing rig and power the system up, simulating a fully ready state with lethal high voltage actively flowing through the closed contactors.
The system is completely live.
Yes, live and dangerous. And then an automated pneumatic machine, or sometimes a heavily glued up technician, physically rips the manual service disconnect switch out as violently and fast as they can.
Wait, they intentionally trigger a catastrophic safety fault on a fully powered live system right there on the factory floor.
Yes, and they have high-speed oscilloscopes attached to the contactors. They measure the exact microsecond the MSD breaks contact, and they measure the exact microsecond the heavy high-voltage contactor snaps open inside the pack.
And the rule is?
That physical-mechanical reaction must happen within that magical 50-millisecond window.
So if I'm putting all this together, it means every single car is practically crash-tested electrically before it ever leaves the factory floor.
Pretty much, yeah.
They don't just mathematically assume the theory works on a computer. They violently force their physical hardware to prove it works under live load.
Exactly. But factory testing, as rigorous as it is still testing brand new, perfectly clean components in a climate-controlled room.
Right. It's an ideal environment.
To guarantee true functional safety, the engineers have to prove the design can survive the absolute worst the real world has to offer continuously over 10 or 15 years.
That is a tall order.
That is the final dimension of our source document. DVP&R, or Design Verification Plan and Report. This is where they take all that perfect engineering and systematically torture it.
Torture testing. This is the stuff that usually makes for great, flashy YouTube videos for car companies, right?
Usually, yeah.
But behind the scenes, reading this document, it is rigorous, brutal statistical science. Let's look at the first torture test from the sources. I'm calling it the electronic hurricane. It is the HIL EMI test.
HL stands for Hardware in the Loop. It is a fascinating testing methodology. Instead of putting a whole physical car on a test track, which introduces too many uncontrollable variables, they take the actual physical BMS computer box and the actual physical wire harnesses, and they plug them directly into a massive supercomputer simulator in a sterile lab.
So the physical brain of the car is plugged into the matrix, essentially.
Yes. The supercomputer feeds the BMS sensor data, tricking the computer into thinking it is driving a real car under extreme chaotic conditions.
Why do that?
The primary goal here is to rigorously test that 150 millisecond software debounce filter we talked about earlier. Remember the magnetic fields from the inverter trying to spoof the PWM heartbeat?
Right, the magnetic induction causing all that high-frequency electrical garbage on the line. The jet engine.
So in this matrix simulation, they simulate insane foot-to-the-floor acceleration. The supercomputer injects incredibly intense high-frequency common mode noise ranging from 10 kilohertz all the way up to 150 kilohertz with massive 1.5-volt chaotic peaks directly into the DC bus lines feeding the BMS.
They are physically blasting the computer's inputs with a hurricane of electromagnetic noise.
Yes. And while this electrical hurricane is screaming at the computer, what do they do to the interlock signal?
I don't know.
The supercomputer simultaneously and randomly injects physical microsecond cuts into the interlock circuit. It digitally simulates the connector violently vibrating over a massive pothole, losing contact for tiny fractions of a second, while simultaneously under maximum electrical acceleration load.
Oh, wow. So they are testing both the PWM noise rejection and the debounce filter at the exact same time under absolute maximum stress.
Exactly. And the pass-fail criteria from the engineers is absolute. The 150 millisecond software filter must have 0 false P0A0D alarms. It cannot mistakenly shut down the simulated car due to the massive magnetic noise, and it cannot shut down due to the microsecond cuts.
It has to perfectly ignore the chaos.
But the absolute moment the supercomputer injects a signal cut that lasts exactly 151 milliseconds, the BMS must trigger the P0A0D error 100% of the time.
It is testing the exact razor's edge of the software logic. It has to ignore the noise perfectly until the exact millisecond the noise becomes a real physical threat. That is incredible.
It's very precise.
But the sources outline another physical test that is even more dramatic because it deals with raw mechanical physics. It is a literal physical race against time, the 100 millisecond gap.
This is undoubtedly one of the most elegant pieces of mechanical engineering in the entire electrical system.
Okay, tell me about it.
When we talk about unplugging a high-voltage connector, say a mechanic grabs the heavy orange plug off the inverter to service it, we have a massive lethal physical problem. The high voltage is actively flowing through the massive copper pins inside that plug. If a human pulls those pins apart while current is actively flowing, the electricity will literally jump the gap through the air to maintain the circuit.
It creates a high-voltage plasma arc.
Yes, a DC plasma arc that can instantly reach thousands of degrees Celsius. It will vaporize the copper pins, melt the plastic housing, and severely burn, blind, or electrocute the mechanic.
Okay, so you absolutely fundamentally cannot allow a live high-voltage connection to be physically separated.
Never.
But the mechanic is standing there, physically pulling the plug out of the socket right now. How does the system stop an action that is already happening?
You use a brilliant, simple physical geometry trick built directly into the plug itself.
A geometry trick.
Yeah. Inside that heavy connector housing, there are the massive, thick, high-voltage pins carrying the main power. And alongside them, there are the tiny low-voltage interlock pins carrying our PWM safety signal.
Okay.
The engineers simply designed the interlock pins to be physically shorter than the high-voltage pins.
Wait, they're physically shorter in length. Why?
Visualize what happens as the mechanic's hand pulls the plug out. Because the interlock pins are shorter, as the plastic housing starts to slide apart, the short low-voltage pins reach the end of their travel and physically lose contact and disconnect first.
Okay.
Meanwhile, because the high-voltage pins are longer, they are still sliding along each other, maintaining solid physical and electrical contact.
Oh, I see it. The shorter pin is a mechanical canary in the coal mine.
Exactly. The engineering specification mandates a specific geometric time gap. When pulled apart at normal human speeds, the short interlock pins must physically disconnect at least 100 milliseconds before the longer high-voltage pins physically separate from each other.
So the short interlock breaks. The PWM heartbeat flatlines. The computer sees the signal drop, and it instantly knows, oh no, a human is actively pulling this live plug apart right now.
Yes, and remember our hardware panic reflex, the 50-millisecond hardwired analog bypass.
The spinal cord reaction.
The instant that short pin breaks, it triggers that 50-millisecond reflex. The hardware comparator races to cut the power to the main battery contactors back at the rear of the car.
So the race is on. The mechanic's arm is pulling the plug, the housing is moving, and the long, live, high-voltage pins are sliding closer and closer to separating and creating that lethal plasma arc. But because the short pin broke first, the computer essentially got a 100-millisecond head start on reality.
Yeah.
And the computer only needs 50 milliseconds to cut the power.
Exactly. By the time the mechanic's hand actually separates the long, high-voltage pins from each other, the line is already completely dead. The contactors at the battery were thrown open 50 milliseconds ago.
Wow.
The lethal plasma arc cannot happen because the power was killed before the physical separation even occurred. It is a simple mechanical geometry trick, buying the computer the exact amount of time it needs to save a human life.
That is just phenomenal design, using a literal difference in physical length to create a safety time travel window.
It's beautiful.
Okay, what about our oldest enemy from the beginning of this deep dive? Micro-fretting, the micrometer vibrations causing rust over years. How do they torture test for something that takes years to develop?
They call this the shake and bake.
The shake and bake. That sounds aggressive.
It is highly aggressive. It is the highly accelerated fretting endurance test. They take the fully assembled fortress connectors, the ones with the CPA locks, the heavy shielded wire, and the floor rubber seals, and they bolt them firmly to a massive 3-axis vibration table in a lab.
3 axis meaning it shakes up and down, left and right, and forward and back simultaneously.
Yes, mimicking the absolute worst chaotic resonance of corrugated dirt roads and potholes. But they don't just shake it at room temperature.
If not.
They put the entire massive vibration table inside a sealed environmental climate chamber. While it is violently shaking, they fluctuate the temperature of the room from negative 40 degrees Celsius deep winter freezing all the way up to positive 85 degrees Celsius, which is about 185 degrees Fahrenheit.
So simulating a car parked in the freezing Arctic tundra and then immediately driven hard across the scorching Mojave Desert.
And they don't change the temperature slowly. They force the climate chamber to swing at a rapid rate of 10 degrees Celsius per minute.
That's thermal shock.
Yes. This causes intense, rapid thermal expansion and contraction of the plastic housings and the metal pins, which causes the pins to shift, warp, and scrape against each other even more aggressively. They run this literal torture chamber continuously for 300 straight hours.
300 hours of violent, chaotic shaking while simultaneously flash freezing and boiling the components. And what has to happen at the end of that for it to pass the DVPNR?
After 300 hours, they pull the connectors out and hook up a high-precision micro-ohm scanner. Despite all the fretting, the violent rubbing, the extreme thermal shock, and the condensation, the dynamic contact resistance of those pins must still register below 0.1 ohms.
A tenth of an ohm. That's practically a rounding error resistance.
Yes, and furthermore, they physically disassemble the plug under a microscope. There can be absolutely no metal peeling on the pins, no microfractures in the plastic locking mechanisms, and the floor rubber seals must still hold a perfect vacuum. If it survives the shake and bake, the engineers can guarantee it will survive the 15-year life cycle of the vehicle.
Which brings us to the final piece of this engineering puzzle, the factory statistics. Because it's one thing to have a team of PhD engineers hand build one golden prototype connector that survives the shake and bake in a lab.
Right. Anyone can build one perfect thing.
Exactly. It's an entirely different thing to build millions of them a year on an assembly line and trust every single one of them with human lives.
Right. And this goes back to the end-of-line 1.0 ohm requirement we discussed in the factory section. In the DVP&R specification, they don't just look at the factory and say, well, most of the packs passed the test, so we're good. They mandate strict statistical proof of manufacturing capability.
Statistical proof.
The specification requires a process capability index, or CPK, of greater than or equal to 1.67 for that 1.0 ohm resistance requirement.
Okay, we need to translate that.
Yeah.
What does a Klapke of 1.67 actually mean in English for someone who isn't a factory statistician?
Think of the manufacturing process like a bell curve. You want all your parts to have low resistance clustered right in the middle of the curve. The 1.0 ohm limit is the absolute edge of the cliff. In the world of statistical quality control, a stake cake of 1.33 is generally considered a capable manufacturing process.
Okay.
But a CPK of 1.67 means your manufacturing process is so tightly controlled, so incredibly precise, that the entire bell curve is squished incredibly thin and far away from that 1.0 ohm cliff.
So it's a measure of how little variation there is between part number 1 and part number 1 million.
Exactly. A CPK of 1.67 mathematically correlates to 6 sigma levels of manufacturing perfection. It means that statistically, out of millions and millions of cars built, the chances of a single defective interlock loop making it out of the factory with a resistance over 1.0 ohm is less than 1 in a million.
Less than 1 in a million. That is the level of mathematical confidence required before they will let you put your family on top of a 1,000-volt power plant.
It has to be. When you are dealing with HVIL safety requirements and high-voltage electricity, the acceptable margin for error is essentially zero.
So, to try and summarize this incredible engineering journey, we started with a terrifying premise, driving around while sitting on massive lethal electrical energy.
Yeah.
And we asked what keeps it safe.
And the answer was way more complicated than a simple fuse.
Way more. We looked at a simple error code, 503 P0A0D, which just sounded like a broken wire.
Yeah.
But what we found wasn't just a wire. We found a highly advanced, noise-canceling digital PWM heartbeat.
Right.
We found a system structurally isolated from magnetic interference by the inverse square law, shielded by Faraday cages, and sealed in Gore-Tex to breathe without rusting. We found brilliant mechanical geometry that uses a short pin to buy the computer a 100-millisecond time travel window to stop electrical fire.
It really is remarkable.
And we found manufacturing processes scrutinized by diamond saws, 3D lasers, and AI cameras to a Six Sigma standard. The P0A0D code isn't just an annoyance on a dashboard. It is the voice of a microscopic, highly engineered guardian, constantly keeping you safe from immense, invisible physical forces.
It really is the pinnacle of modern automotive functional safety engineering. The sheer depth of complexity hidden behind a simple plastic orange plug is truly staggering.
It is. And I want to leave you, the listener, with a final provocative thought to mull over. We've spent this entire deep dive talking about physical things. Physical pins rubbing gold plating on physical wires being routed away from magnetic fields, physical water being blocked by Gore-Tex, and physical geometry buying us 100 milliseconds of safety.
Very tangible things.
But the automotive industry is evolving rapidly. We are moving towards wireless EV charging technologies, and there is heavy research into completely solid-state battery architectures and wireless data transmission within the car's harness itself. In a future where physical connections might become entirely virtual or rely purely on magnetic resonance fields, how will engineers build a physical tripwire when there is no physical wire left to trip?
That is the big question.
How do you ensure a 50-millisecond foolproof hardware panic reflex when the hardware itself is just a wireless signal moving through the air?
That transition from physical validation to wireless functional safety is absolutely the next great frontier for automotive engineering. It's going to require a whole new set of rules.
It is going to be wild to watch it unfold. Thank you for joining us on this deep dive. I guarantee the next time you look under the hood of an EV or see a mechanic unplugging a massive orange cable, you are going to look at those humble plastic connectors entirely differently. Until next time.